Okay, good day. This is Math 130 Intro to Statistics. I'm Professor McCulley. This is lesson number 21, confidence intervals for proportion. So let's get to it. Today we're going to find the point estimate for population proportion. We're going to construct and interpret confidence intervals for a population proportion, and we're going to determine the minimum sample size required when estimating a population proportion. Okay, so first, definition: the probability of success in a single trial of a binomial experiment is P, and that is known as the population proportion. So the point estimate for P in a population proportion of successes is given by the portion of successes in a sample denoted by P with this little uh, arrow over the top of it, and the X over N, where X is the number of successes in the sample, N is the sample size. The point estimate for the population of failures is Q with a little arrow over the top of it, equal to -1 minus P with a little arrow over the top of it. And those little arrow symbols are, I kid you not, P hat and Q hat. So when you see this symbol, you are going to say P hat. Can you believe it? Okay, so quickly, in a survey of 500 swimmers, 275 said that they thought the butterfly was most difficult. Find a point estimate for the population proportion of swimmers who think that butterfly is the most difficult. So P hat is equal to X, the number of successes in our trial, over the number of elements in the sample. And so we're going to say that our successes are 275 over the 500 total, and that turns out to be 0.55 or 55%. All right, pretty easy for the first one. A confidence interval for the population proportion P is defined. So P is going to be our population proportion, and it's going to be our point estimate minus a margin of error. And P will be between the point estimate plus the margin of error. And so we're starting to get into a little bit of some commonality here. But this time our margin of error is going to be a z statistic times the square root of p hat times q hat over n. And again, you might see something similar to this earlier on when we're talking about probability of success and failure. All right, so the probability that the confidence interval contains P is C, and whatever C confidence level is, 90%, 95%, 99%, depending on what they ask, assuming that the estimation process is repeated a large number of times. All right, so if we're going to construct a confidence interval for population proportion, we're going to identify the sample statistics, N and X. We're going to find that point estimate. We already done one like that. We're going to verify that the sampling distribution of p hat can be approximated by a normal distribution. And for us to do that, again, we're going to have our number of elements in the sample times the point estimate. P hat, and that has to be greater than 5. That's something we've seen kind of before. And then when we're doing using the normal to approximate binomial distributions, and then n times q, and again q hat's going to be 1 minus p hat, and that has to be greater than 5. We need to find that critical value for ZC that corresponds to the given level of confidence, and we have those ZC scores that we've already found, but we can calculate them again if we want to. But we made a list of them when we were doing the critical numbers for z-scores. And then we're going to find that marginal error. E equals z sub c times the square root of p hat times q hat all over n. We'll find those right and left endpoints. And then as a practical matter, we can use the graphing calculator with this one prop z interval. function in the stat and then test menu, and you'll have to go down a little bit to get to it. Okay, so the next example that we're going to do is we're going to use the data from the swimmer question to find a 95% confidence interval for the population proportion of swimmers who find butterfly to be the most difficult stroke. So all we're going to do is we're going to go through this step-by-step list, and we're going to identify, number one, we're going to identify the sample statistics N and X. We already did that in the last particular section. So one, the number of people that are in the sample is 500, and we said that there's an X that was 275, and we already calculated the number two says we're going to calculate the point estimate p hat, and we did that in a previous one, our previous part as well. So p hat is 0.55. Step 3 says verify the sampling distribution of p hat can be approximated by the normal distribution, and clearly if I go n p hat here, clearly if I go 500 times 0.55, so let's just say as a for instance, this is 0.50, which is lower than 55. 0.5 times 500 is, this is saying 500 times a half. Half of 100 is 250. And that is clearly going to be bigger than the 5 that I need. So clearly that's going to be bigger than the 5 that I need. And n q hat would be 500 times 0.45. And remember, if p hat is 0.55, then q hat, let's do this correctly, q hat is going to be 1 minus 0.55, which would be 0.45. And so again, even though this is a little bit less, it's going than 0.5. If we round it up to 0.5, half of 500 is 250. And even though we lower it by that 5%, it isn't going to be down to below 5, and that's clearly greater than 5. So we checked our suppositions there. And then we verified our assumptions. And then we're going to find the critical value for ZC that corresponds to the given level of confidence. Okay, so if we want to find a 95% confidence level, and remember this is a two-tailed test because it's a proportion, and so if I say it's a 95% confidence, this is going to be 2.5%, and this is going to be 2.5%, and from the table that we made in the previous section for confidence levels, this Z-score here, this ZC is 1.96. Now, if you don't have that available to you, that table, or you forget, you can calculate that with an inverse norm on your calculator. So if I grab my calculator, and the inverse norm is in the distribution menu. So second, hit the vars button, and inverse norm is 3. Now, if we want to find the area to the left, and we're thinking about it this way, we want to find this ZC score here. If we're doing it from the left, and if you're doing a TI-83, you're going to have to do it this way. Anyway, this area here, if this area that's in this portion here is 2.5%, what's left is going to be 97.5%. So if I want to find that, my area is going to be 97.5 or 0.975, and then the mean 0, standard deviation 1, and we just go down here to paste, and if we hit enter and go to inverse norm, and again you can see 1.95996, and so if I'm rounding it to 4 decimal places, I look at the 6 is above 5, that rounds this 9 up, that'll round that 9 up, which will round the 5 up. And so I'll have 1.9600, which is what I have right here. And so let's see, number 4, it says find the critical value. So my ZC value, oops, didn't want to do that. My ZC value is going to be 1.9600. Then if we go to the 5, find the margin of error, and the margin of error follows this equation right here. So number 5, margin of error is going to be a ZC score. Oops, I'm sorry. That's wrong. Oh, don't lose all of it. Margin of error, E, is, in that equation we gave in a previous slide, ZC times the square root of P hat Q hat all over N. In this case, it's the ZC score, P hat Q hat all over N. In this case, the ZC score was 0.9600. Square root 0.55 was P hat right there, times 0.45, which is Q hat right there, all over N, the total number 500. And so we get, if we do that calculation, we get 0.04361. And if you need me to do that calculation, I can do it in class. But this looks pretty small, and that's okay, because remember, we're doing a population proportion, and the P can only be between 0 and 1. So this has to be very small for our margin of error. All right, so number 6, let's go back here. Come on. Uh-oh, it's locking up on me. Please stop. Not responding. Here we go. So our left and right endpoints is going to be P hat minus the margin of error less than or equal to the actual proportion less than or equal to P hat plus E. And then as a practical matter, we're going to do the 1 proportion Z interval here in a moment. But once we have that calculation, so 6, our margin of error is going to be our point estimate minus the margin of error less than the actual population proportion, and then P hat plus the margin of error. And the way that looks, remember, P hat was 0.55 minus 0.04361 less than P, and then 0.55 P hat again plus 0.04361. And then I did those calculations, and it turns out to be 0.50639 less than the population proportion, and I need a less than there, less than, and then when I do this addition, I get 0.59361, and that is my 95% confidence interval. So if I'm writing a conclusion, I can say that my conclusion is that the actual proportion of swimmers who find butterfly to be the most difficult stroke, we are 95% sure that that value lies somewhere between 0.506 and 0.593. Now, if we want to use the graphing calculator to do that, it's fairly straightforward. You can go to this, and it's not in the distribution menu. It's actually in the stat menu. So I'm going to go second stat. Oops, I just need to go stat. Sorry about that. Just hit the stat button. Go over to tests, and it's not in these first 10. So you got to arrow down or go to, you could go alpha A, and this is a 1 proportion Z interval. And so we're going to hit enter there. And so I have all the values in there. The value for X is 275, said that butterfly was the most difficult out of a sample size of 500 and a confidence level of 95%. So we can just bop down to calculate, hit enter, and again, you can see that 0.50639 and 0.59361 match up what we have there. Okay, so next, finding the minimum sample size estimate to P. Given a C confidence interval and a margin of error E, the minimum sample size that you need to estimate the population proportion P is N equal to the point estimate times the point estimate for proportion times the complement of that times the z-score squared divided by the margin, the z-score divided by the margin of error all squared. This formula assumes that you have preliminary estimates of p hat and q hat, but if you don't have those preliminary estimates, you can make p hat 0.5 and q hat 0.5. So you get a little bit of wiggle room there. So if we want to do our next question, we could say, do we have a big enough sample size to make the conclusions that we made in the previous example? So is our sample size actually big enough to do to make this confidence interval that we came up with? Well, if our n so if we want to figure out what our sample size should be, we're going to go that it was, let me write the equation down. It was p hat times q hat times the z-score over the margin of error squared. And so in this particular case, we have 0.55 times 0.45 times the z-score, which was 1.960, over the margin of error, which was 0.4. Oops, I'm sorry. It was, come on, don't delete the whole thing. 1.960 over 0.04361. All right, quantity squared. So let's put that in our graphing calculator. We'll clear that. It was 0.55 times 0.45 times parenthesis 1.96 divided by 0.04361 quantity squared. Hit enter, and I get 499.9. Okay, so 0.9369. So 499.9369, and our sample size is 500. So yes, we have just enough. Well, that's all I got today. So our Marvel fun fact of the day: in Spider-Man Homecoming, Peter Parker is known to be a 15-year-old sophomore. And so I'm assuming that the Spider-Man movies for the Sony Marvel Universe will be like a Hogwarts thing where he goes his sophomore, junior, and senior year before they move on to a new Spider-Man. Excuse me. Well, that's all I got. Have a good day.